All right, let's move to chapter 10 on refrigeration. And in this first lecture, lecture 27, we're going to cover 10.1 to 10.3. Basically, give you an introduction on refrigeration systems, vapor-based refrigeration systems. Then I'll show you the thermodynamic cycles for vapor compression refrigeration systems and properties of refrigerants in this first lecture. All right. So let's go back to what we learned about Carnot refrigeration cycles when we were looking at cycles. You know that the purpose of a refrigeration system is to maintain a cold region and a temperature below that of its surroundings. And you can use this for air conditioning, or you can use this in a closed refrigerator, in a closed box, which imposes different conditions, of course. Air conditioning has a smaller delta T between ambient and the actual piece that you want to refrigerate, but it has a higher heat load because you have to take away the heat load from people and other things that heat the room. A refrigerator, on the other hand, has a lower heat load, but you want to be able to go to lower temperatures. Anyway, in all of these cases, you know that based on the second law, you need to add mechanical work to this system to maintain that body at a temperature lower than its surroundings, because there's always heat that's going to come from the surroundings to try to increase the temperature of the body in question. And the simplest cycle that we have is then the Carnot cycle. So in the case of the Carnot cycle, you had a hot side reservoir, and you had a cold side reservoir. And if you remember, the only thing that mattered there is the actual temperatures of the cold side and the temperature of the hot side. So here, we were taking heat out of the cold side region in an isothermal way, which is unphysical, but it's idealized. And then we were then making a transformation. We were dumping this heat onto the hot side in a also isothermal way, which is also idealized. So what you had in a TS diagram is an isotherm between 4 and 1, which is the heat being taken out. Then here we had some idealized isentrope, an isentropic transformation between 1 and 2. Here we had 2 to 3 isothermal, and 3 to 4, again, isentropic. So this cycle, in essence, if I summarize it here, you have isentropic compression from some region where you had a certain amount of quality to your liquid-vapor mixture, to, let's say, saturated vapor, point number 2. Then, so this takes work that has to be done on the fluid. Then going from 2 to 3 is a transformation. 2 to 3 happens in the condenser, so you go from saturated vapor to saturated liquid in point number 3, isothermally, of course. Then you go through a second isentropic transformation, 3 to 4, in this particular case a turbine that gets work out. So now, again, we are here at the point where we have a certain quality to the liquid vapor mixture that we have, and this then is used. So this fluid is evaporated. The amount of vapor phase material is increased in the mixture. This evaporation of material is what is actually cooling the surroundings. So the work done by the system, of course, is 1 to 2 to 3 to 4 to 1. That is the net work that you had to add into the system. And the heat, the useful heat that you get out, is from B to 4 to 1 to A. I moved on to the next slide a little bit by accident, but we can say the same thing. And then we have here the COP. The COP is the amount of net heat that you get out. So B41A, that's useful heat pumped out of the system. And the work that you had to pay for this is 1, 2, 3, 4. So this is what we have here. The COP, which is the net heat in divided by the net work you had to give to the system, is the area of 1AB41 divided by the area of 12341. All right, that's Carnot. So basically, I'm repeating here, the net heat transfer and the net work in. Now, this was an ideal cycle. Of course, we don't have Carnot. So there are a number of departures from the ideal Carnot cycle. The first one is the fact that the heat transfer between the refrigerant and the two regions, the hot side and the cold side, cannot happen isothermally. There has to be a finite delta T to drive this heat. So to be able to pump heat out of the surroundings, you have to have your cycle that works here, but it has to be colder than the actual temperature of the cold side region. In other words, heat transfer can only go from a higher temperature to a lower temperature. There's an arrow to heat transfer. If you want to keep your cold side at this temperature here, indicated by my cursor, you have to have the evaporator of your refrigeration cycle at a lower temperature here, so the heat can go from this temperature down to that temperature. That is an irreversible loss. In the same way, if you want to reject heat from your cycle between 2' and 3' to the temperature of your heat exchanger, to the outside air, for example, if you want to refrigerate, then you have to have this heat transfer occur between TH' and TH, and that again is an irreversible loss. Second source of irreversible losses are these things, which we don't really like. In fact, they don't have to have irreversible, but this is something that we are not going to be tolerating. And that is namely that in this particular case, we are here compressing from 1 to 2' in a wet regime. So basically, you have a finite quality to your liquid vapor mixture here that you get to a saturated vapor. But the problem is that you're going to be pumping here on a mixture of particles of liquid in a gas, which is something that will wear out the turbine blades or the compressor pistons. As we have seen before, this is to be avoided. Wet compression is to be avoided. The third thing that's not particularly useful is the transformation from 3 to 4, or 3' to 4'. Essentially, first of all, it's again work done by the system, but that work is done in a two-phase regime. So whatever machine you're going to be putting there will be worn out quite quickly because the droplets erode the blades. Secondly, it is so that very little energy is actually in practice recovered by the work done between 3 and 4, and that means that you have here a system that's actually quite an expensive machine for little benefit. Typically, you don't do that. You avoid it. Now, that means that the ideal coefficient of performance, which was this ideal, basically, Carnot cycle that would go between this point, this point, this point, and that point, is completely different from what is going to happen in practice, and the real efficiency is going to be less than this ideal cycle. So let's take a little look at what an actual refrigeration cycle looks like, and we'll still call it ideal because there are going to be additional losses compared to what we have here. So here is reality. We still have the compressor between 1 and 2, and it will take work in, but we're not going to put it between inside the vapor dome. We're not going to put it between a point 1 that is at some quality of the liquid vapor mixture and point 2, which would be a saturated vapor. We're going to put it entirely in the vapor phase between 1 and 2 here first. So that's the first departure. Because once you're here, this is an isobar. Once you're on this isobar, you can't make a square cycle anymore. Now, 2 to 3, we're then going to first cool down the vapor and then condense the vapor into a liquid to get to saturated liquid at point number 2. And here we have taken out this turbine that did work. We're just going to put an expansion valve, which means that we're going to go through an isenthalpic transformation between 3 and somewhere here, point number 4. Point number 4 then is an isothermal transfer of heat between this and saturated vapor at point number 1. So if we make the count of our enthalpies, the compression work required is going to be H2 minus H1. The heat exchanged on the hot side in the condenser is going to be H2 minus H3. That's here. An expansion valve is just an isenthalpic transformation, constant enthalpy. So H3 equals H4, and nothing happens there. No work, no heat. And then we have Qin over M, that is the heat that you're going to be able to take out in the evaporator. That is the useful work, well, sorry, the useful quantity that we want for a refrigeration cycle is cold. So it's Qin over m dot, and that is H1 minus H4. So here is our cycle. We then have a few nomenclature things. The useful thing that we get out of a refrigeration cycle is a refrigeration capacity, H1 minus H4. The price we have to pay for it is H2 minus H1. That's the work in the compressor. The heat rejected somewhere in the back of your refrigerator is H3 minus H2. And then this useless valve, basically, the throttle, is H4 equals H3. But you need it because you need the pressure drop. So the COP from these four is H1 minus H4 over H2 minus H1. H2 or H2S, because for the moment we have only considered our machine to be an isentropic one, our compressor to be isentropic. Now, this refrigeration capacity is customarily expressed as either in international units, kilowatts, or in English units. You will find some air conditioners in BTU per hour, which is fine. And there is a rather strange unit that's sometimes used, that is used, the ton of refrigeration, which, I'll read for you what I wrote down, is the rate of heat transfers that results in the melting of 1 short ton, 907 kilo, of pure ice at 0 degrees centigrade in 24 hours. What it amounts to is 12,000 BTU per hour, or 3.5 kilowatts. Okay, now let's take a little look at other irreversibilities. So what are the irreversible things? First of all, you're not necessarily always going to be at a saturated liquid here, a saturated vapor here. You don't really know where you're going to end up, and it depends on the outside temperature and many, many other things. Second, this compressor is not an isentropic compressor. Instead of going from 1 to 2S, you go from 1 to 2, and then, of course, you have to correct that for the isentropic efficiency of the compressor, like we have been doing for every single machine since chapter 8. So here is the isentropic efficiency. Third, you condense, but who knows that you're going to stop at saturated liquid. You may undercool it a little bit. It's another departure from Carnot. And then, of course, the ultimate loss is this throttle, which does nothing useful. So if I go in the real cycle and I now summarize all the irreversibilities, we have, as we saw before, the irreversibilities that are accompanying the heat transfer. In other words, on the hot side, your cycle has to be hotter at every point than the ambient air so that heat can transfer from the cycle to the ambient air. On the cold side, your cycle has to be colder than whatever it is you want to refrigerate so that the heat can leave whatever it is you want to refrigerate and end up in the cycle. You then have the irreversibilities in compression during 1 and 2. And you have the fact that you are actually working in saturated vapor here instead of right exactly on well, you're not working in saturated vapor, you're working in superheated vapor instead of exactly in saturated vapor. The same thing here, you can be a little bit in undercooled liquid instead of exactly at saturated liquid. And of course, the ultimate loss is the process 324, which is just a throttle that does no work at all, but it's just throwing away that work, that potential work. Instead of going vertically, which would have given you an isentropic work, we're going sideways because it's a lot cheaper to make a crimp in a tube, which is a throttle, rather than add an additional machine. Okay, now let's move into the selection of the refrigerants. So before we get into that, we have to look at another way that's historically used to characterize refrigerants, because it has practical implications. We have explained everything on the basis of TS diagrams, like we use for the Rankine cycle, for the Brayton cycle, and so on. Well, let's move into something called the pH diagram, which is a little bit historical. So we go from 1 to 2, the isentropic compression. In a pH diagram, you go from 1 to 2. So remember, the enthalpy expended to get to 2S is less than the enthalpy you really have to expend to get to 2. So the H-axis This is shifted down a little bit, but it's hypothetically an isothermal, an isobaric process. This is the isobar. So this is a little horizontal like this. And then all this happens along an isobar. 2 to 3 is an isobar. There we go. And we have a little bit of undercooling here. We have a little bit of undercooling here. This is a vapor dome in a pH diagram, corresponds to this one here. So we are here. The nice thing about a pH diagram is that an isenthalpic transformation, a throttle, is now a vertical line, 3 to 4, because this is enthalpy. Here you have point number 4, so at the finite quality factor, and you go from 4 to 1 at constant pressure, because this entire thing here is a constant pressure. So you have a diagram that looks like this, 1, 2, 3, 4. The nice thing is that it gives you a direct measurement of pressures, and pressures are very important in selecting refrigerants. So another thing that matters, the isotherms that were horizontals here correspond to these curved things here on this, whereas the isentropes correspond to these curved, these straight things up there. But these are the isotherms. Okay, so let's look at the criteria that enter the selection of a refrigerant. First of all, of course, the temperatures of cold and warm regions must correspond to what you want from the system. Temperature of the warm has to be a little higher than the ambient temperature where you're going to reject your heat, or if you do it in a different cycle, it has to be warmer than wherever it is you're going to reject your heat. The average temperature of the cold side has to be colder than where you want to take the heat out of. Now, the selection is based on PT and pH for the range of applications. Basically, there are two considerations here. You don't want to have too high a pressure at the highest pressure point of your system, which in this case is site number 2, 3, because if you have a much higher pressure, your compressor is going to cost more. You're going to have higher temperatures, so you may have to change the metal in the compressor to take the higher temperatures. You are going to have to seal these materials, and so your seals can work better at lower pressure because there's less force working on the rubbers. So if you go to a higher pressure, you're going to have your refrigerant leak out. And these refrigerant systems are sealed and stay functioning for 30 years or something, so you really don't want that either. The other thing you don't want is to work below atmospheric pressure, because if there is a leak and you're below atmospheric pressure, the air will go in and contaminate your refrigerant, and the machine, again, will not work too well. So you have to look at the temperatures, and you have to try to keep your pressures in a range that are reasonable. A reasonable pressure here is, of course, 1 atmosphere or just a little bit above to minimize leaks in. A reasonable pressure here is really set by temperatures, and so 10, 20 bar, well, 10, 15 bar is a good number, so you can still build the housing out of aluminum because the temperature are below 400 centigrade, 300 centigrade. If you go to much too high a temperature, you're going to have to use steels, and these machines become much heavier and more expensive. So 10, 15 bar is a good number, 100 bar is not a good number. And that dictates now the selection of the refrigerants. So bear in mind that refrigeration has a nice and long history. It was used typically in fishing boats to be able to go far out into the ocean for the catch and then put the caught fish on ice. But in the beginning, between the 19th century was invented and World War II, roughly, refrigeration cycles used, well, carbon dioxide, which makes sulfuric acid, and NH3, which is ammonia. These things are dangerous, corrosive, toxic, and so on. So it was okay on fishing boats because they were on deck, and if they exploded, that dirty stuff went out in the atmosphere. But it's totally unusable in closed spaces, of course, and so this was very quickly abandoned. The big breakthrough came in the mid-30s, late 30s. A guy called Midgley invented something that were called the Freons. These are chlorine-containing chlorofluorocarbons, CFCs, and the typical refrigerant for that is Freon. Freon was refrigerant 12, Freon 12, carbon, 2 chlorines, 2 fluorines. Looks like carbon tetrachloride, but with 2 chlorines substituted by fluorine. Okay, so that was great because it's extremely stable and it's absolutely non-toxic and non-dangerous, but it had a problem, and that is that it attacked the ozone layer that's around the poles and protects the Earth from ultraviolet light. So chlorine is essentially a catalyst that decomposes ozone, O3, into oxygen, and with that, the ultraviolet rays that come from the sun could penetrate deeper into the Earth, and people got skin cancers. So this then was banned in the late 70s, I think, or something like this, and replaced by refrigerant 134A, which is a mixture, which is a fluorine-based tetracarbon. Okay, that's what we still use. It has another problem. It is a strong greenhouse gas, but we still use it. Replacements have been sought. They try to go to CO2, but the problem with CO2 is that it's supercritical fluid at 31 degrees C. So you had to work above the vapor dome, which doesn't work. So then you had to undercool it with other means. One notion was to go back to ammonia, which we still actually used in large industrial systems, but it's unusable, of course, for consumer products. And then we have hydrocarbons, typically propane or methane. They're fine, but they're flammable, so one has to be a little careful there too. So here is a summary of the properties of the refrigerants. R12, which was Freon, is banned. You cannot buy R12 legally in the United States and I think worldwide, but I don't really know that. What we use now in automotive is R134A, often also used as R22. I think it's mostly in residential air conditioning, but I'm not quite sure. There are a number of them that are blends, and then carbon dioxide is attempted. It has less of a greenhouse effect than R134A, but still, and of course, it's carbon dioxide. Problem there is this goes supercritical. And there are a number of options that are actually easier to use that we give here. Natural, well, it's not because it's natural, of course, that it's not toxic. So one has still to be quite careful. Thank you.